Okay. Can you hear me now?
Yeah, we can hear you.
You can hear me. Great. I'm going to put this down. And you guys can see me as well?
I don't have any video feed.
Yeah, we can't see you quite yet.
Okay.
Oh, now we can. Yep.
Good morning, all.
Good morning. So we
Hi.
normally start at 5 minutes after the start time to give people time to sort out Zoom issues and log on. But if you wanted to test sharing slides, we could do that real quick.
Yes, I will do that. Good morning, folks. Can you see my slides now?
Yeah, they look great.
I'll go to full screen mode. How many do we typically have on the line here, and where are you? Are you all over the country, or are you in like Michigan, or what's the deal?
All over the place. We have a strong concentration from Michigan, and then we also have a strong concentration from Livermore and Los Alamos. But whenever we do the morning lecture, they tend to watch the recording later in the day. Yeah, so we normally average 60 people in person when we lecture at 3 p.m. Eastern, and then probably another 50 to 100 will view the lecture recording later in the day.
Okay, good. Hey, a dumb question. I know as I look at the screen, I can see my slide, but I see a bunch of you on the right-hand side. As you're looking at the screen, do you see a bunch of you on? Are you seeing yourselves from my screen also, or not?
We don't see ourselves on your screen. We just see, but we do see ourselves on our own screens.
Okay, thank you. Okay, I'm just going to get some water, and then we can start when you want me to.
Sounds good. Thank you.
As the meeting host, can you mute everybody?
Yes. And then I will also, if there are questions during the talk, clarifying questions, I'll chime in and ask them. Otherwise, we'll save them for the end.
And what time would you like me to finish by?
Whatever pace that you normally go at. With lectures typically range between 30 and 45 minutes, and then we take the remaining portion for questions.
Very good. Has this group heard any other talks in the last week or so related to the his 75 years of Trinity?
Not in the last 2 weeks, but earlier this summer we had Alan Carr, the historian, talk to us about the Manhattan Project. And then we had Jessen talk to us last week about the DAF, the Device Assembly Facility, and their capabilities there, and just a small amount of the history of the tests that were done there.
Right, right. Shall I get going, or would you like me to wait a little bit more?
We normally start at 5 minutes after, so what I'll do is formally introduce you at 11:04, and then we'll be good to go from there.
Sounds good. Thank you.
Because it's 11:04 now, so I guess to the audience, yeah, we're very lucky to have Dr. Mark Chadwick with us here today. He's the Chief Scientist and Chief Operating Officer for the Weapons Physics Division at Los Alamos National Laboratory. And if you've ever used NDEF cross-sections or simulations using them, then you have Mark to thank and to cite. So like I said, we're lucky, and I'm excited to hear this talk. So Mark, the floor is yours.
Okay, well, thank you for inviting me to give this talk. It's one I've given a few times in the last few weeks, and I put it together because of my interest in the history of nuclear science. And we'll be talking about, hold on. Sorry, I'm just expecting to be able to page down, and that's not working, so. Okay, excuse me, I'm going to proceed here with, here's a quick overview of what I want to cover. I'll be talking a little bit about both critical mass calculations, including a simple formula that was used during the war, and a summary of the cross-section developments between sort of 1940 and 1945. I'll cover how little was known initially, but they had tremendously good intuition, of course. They understood that certain phenomena, like the multiplicity of neutrons emitted in fission, or the fission spectrum energy dependence, they had a good intuition that those kind of things would be very similar for fast neutrons that they knew they needed to care about versus thermal neutrons, and knew that they could use thermal measurements to their advantage in some cases because of the higher cross sections and better statistics. They also, importantly, had a good guess that plutonium would be at least as good as uranium-235 as a fission material. We'll talk about some of the disappointments they had, that some of the cross sections were lower than they wanted, like fission, and of course, plutonium spontaneous fission was an important part of the story. The history will involve the importance of the British connection early on, and then really through the Manhattan Project. And there's some interesting historical books. I'll give a summary at the end, but for example, Los Alamos really wrote the book literally. Robert Wilson was the second division leader of the physics division, and he put this nice summary of everything that was learned, called Nuclear Physics, LA 109, after the war, around 1947. And at least by that era, pretty much everything that had been compiled together was from Los Alamos. And of course, today, numerous institutions across the lab and the world contribute in important ways. Part of what I'll do in this talk is compare against our modern understanding of these quantities. And a little bit of a theme early on was, dare I ask, was Oppenheimer sloppy? That's a kind of sacrilegious thing to say in Los Alamos, but I'll give you a hint of why I bring that up. We'll start off with a conference that got Los Alamos going March and April 1943. It's documented in a remarkable document we have in our vault downstairs, LA2. As you saw at the beginning of this talk, it's an unclassified talk, but extracts from classified documents have been declassified that I'm sharing with you. And these are the minutes from that first meeting. And you can see the various topics that they knew they needed to cover to pull off a wartime bomb. And I'll be focusing really on the first three topics: the status of knowledge then, some of the experimental capabilities they needed to build, and especially how the fission and fundamental constants affect the critical masses. Here I want to remind you about the two approaches that were pursued in Los Alamos in the Manhattan Project for the bomb. There's the uranium path and the plutonium path. We'll start off with looking at the uranium path, which was, in today's language, the higher TRL solution, the higher technical readiness level solution. They knew from the beginning that there was a reasonable chance they could pull this off. The story, as you know, starts with Einstein's letter to Szilard after this discovery of fission. This image of a fissioning uranium nucleus is actually a calculation from our theoretical division on the shape of the nucleus as it fissions by Peter Muller. And in 1940, the British wrote an important memorandum between Frisch and Piles, which outlined their reasons for believing that one could make a fast critical mass of uranium and make a bomb. That was taken up by the British government in something called the Maud Committee that wrote a very, in fact, if you read it, it's very impressive, a very impressive summary of what was known about uranium, both as a neutronic fissionable material and the ability to separate the isotope from natural uranium. That was put together. Sir James Chadwick was the writer of the final version of that. And as he shared that report with the Americans around 1941, he had made a comment that, in his view, if you could get enough of the separated 235, there was a 90% chance of an efficient explosion. So they were confident from the beginning that they could, if they could get the material, pull off a gun bomb. And then I told you about the conference at Los Alamos that started the project in Los Alamos, where there was, a fairly high confidence level in uranium. Plutonium was discovered around 1940, and this is a picture of Segre. Macmillan was the Nobel Prize winner with Segre for this, but this is actually a picture of Art Wall, who was a collaborator and longtime employee at Los Alamos as well. The ability for plutonium to be used really took off once Fermi showed that you could produce a reactor, a pile, and that allowed a pathway to make plutonium in reactors, which was ultimately an easier way to separate and produce the 239 plutonium. So over this period, there was a growing enthusiasm for plutonium. It was being produced at the reactors of Hanford that were stood up. Material wasn't actually coming to Los Alamos until 1945, really, from Hanford. But in the summer of 1944, there was this discovery from Segre about the importance of 240 plutonium spontaneous fission. And that led people to realize that one couldn't make a gun bomb out of plutonium. There was tremendous disappointment at that point. I've heard stories that Oppenheimer offered his resignation to Groves. He was so disappointed. But that remarkably led the lab to completely reorganize and restructure. Oppenheimer really was a tremendously effective manager, and he completely restructured the lab. He created a gadget division for the implosion project. The first physics division leader, who we'll hear about later, called Backer, he was moved to run that gadget division, and Robert Wilson took over the physics division at that point. That's when they realized they could make an implosion, really, and tremendous advances were made. This was a quote from Christie on the theoretical advantages of a implosion weapon to make a more efficient explosion. And optimism increased during this period. And of course, we'll get to the nuclear test of Trinity itself to prove out the concept. during this time, you know, the uranium went up and down in its usefulness. It was always viewed as kind of a safe option. In fact, once the implosion approach really took off, OPIS suggested that we start redirecting uranium resources to use uranium in a implosion instead of in a gun bomb. And this is the point here where Groves said, sort of, hell no, you know, you've made a lot of progress already. I don't want you to give up on the uranium gun bomb. Keep at it. So we'll talk about the nuclear physics now during this project, but I'd like to start with some quotes from Robert Wilson in his nice summary after the war. I'll let you read them, but here he's just reminding the kind of circumstances that they were working and the pressure they were working on to pull this off. I think this middle one is quite interesting about how they were constantly worried about unpredicted or overlooked mechanisms that might catch them out. And because of this, they actually pursued numerous complementary approaches, and those complementary approaches really proved very profitable. It was a time when the lab scrounged equipment from around the country. So Wisconsin was doing some fantastic work with a Van de Graaff machine, and had discovered the value of making neutrons through the lithium PN reaction as a source of neutrons in the fast MeV range. That was particularly important because that range up to a couple of MeV was very relevant to the neutron energies important in a fission bomb. And so we brought in scientists from all these different labs, but not just the scientists, we brought in their equipment. So we moved Cockcroft-Walton accelerators, cyclotrons from Harvard, from Princeton. We also built a reactor. It was a thermal reactor to provide some thermal neutrons. And we also used a number of very useful static sources like radium beryllium, where the gamma rays make beryllium neutrons. So neutron sources from a number of different pieces of equipment. Sorry, excuse me. Just some nomenclature. 235 uranium, often called at Los Alamos U5, often called in the early days 25, 2 from the 92 and 5 from the 235. So plutonium becomes 49, 4 from 94, and 9 from 239. If you read the early documents, you'll find that's how they refer to things. So for example, some of you may have Serber's Primer book on your shelves. This was kind of a summary of what they knew in 1943 from a meeting at Berkeley. In that book, there's a picture of what they knew on the cross sections. 49 is plutonium, 25 is uranium. This is a log plot, so 6 is 1 MeV. You see the threshold for 238 here. That's pretty much correct. The cross sections here, at that point they thought uranium 235 was about 1.5 barns in this region. We'll see it's actually a little bit lower now. They thought that plutonium was twice as high. That was pretty optimistic, and we'll see the consequences of that. The people on the right-hand side at Fuller Lodge, you can see Serber. I think this is Nick Metropolis, Carson Mark, a Canadian who led the theoretical division for a long time. We'll talk next about critical masses. Of course, as you will all know, if we want to calculate a critical mass, we can just do a search on a transport code like MCMP or Partisan using very sophisticated cross-sections, NDEF cross-sections, very high fidelity, vast numbers of groups of different energies, angles, lots of resonances included, many different reactions. We'll run millions of histories if it's a Monte Carlo calculation. And this will give us a pretty accurate estimate of what the critical mass is. What they were doing back in 1943 was analytic formulas. They had a formula here. This is actually from Oppenheimer's write-up of the objectives and a global summary of sort of what we knew at the time from that first day of the meeting. And he talks about the critical mass bare, being dependent on various quantities, the mass, Avogadro's constant, something called the transport cross-section we'll talk about. There's other cross-sections, the fission cross-section, the density, the multiplicity nu bar, and various correction factors here. This actually comes from early work that started with Rudolf Piles, published in the Proceedings of the Cambridge Philosophical Society from 1939, with various refinements to that work. A number of people, including Serber in the US, were involved in those refinements. This kind of formula was used by the Maud committee that I mentioned earlier in their estimates of the critical mass as well. And when you put in what they believe they knew for these constants, then you'll get numbers like 60 kilograms. In fact, that's a mistake. If you put those numbers into the right formula, you get a slightly higher number. But that's to be compared with some of our best estimates today. So if you take pure 235 in a simulation of MCMP with our best cross sections, you'll get 47 kilograms for the 235 pure critical mass, pure 235 bare. And of course, those data have been actually calibrated to match integral criticality experiments, the Godiva experiment from Los Alamos, which is a sphere of 235 uranium, well, HEU. So it's not pure simulation and theory, it's been calibrated to data. If you look at plutonium, you'll get a number like 15 kilograms for that, whereas today we'll get more like 10 kilograms. And they had formulas both for bare and for tamped critical masses. Think of this as an infinitely tamped critical mass. Another example, look at the tamped critical mass that they were estimating for plutonium. Here they give 4 kilograms. When we use pure alpha phase plutonium at about 19 grams per centimeters cubed, in our best estimates today, we get 4 as well. So they did extremely well, kind of remarkably well. It's, as I'll show in this talk, they were very lucky. They had a large number of compensating errors. But if we look at this formula, what we find is that the formulas they wrote down, that Oppie wrote down, are full of typos. I won't go through here all the typos, but it's kind of frustrating. If you try to compute this, you'll figure out the typos, and then you'll have to figure out what the right formula is. And in the same summary paper, we have a report from Beta, which I'll get to. But that brings up this sloppiness of pi. And in fact, in Serber's primer, he talks about how Oppie was actually famous for such issues. Here he's comparing Dirac's writing, where everything is elegant and beautiful. But when it comes to Oppie, some part might be off by a factor of pi or something like that. The little things might not be quite right. And then he goes on to say how the important stuff is always right. If we look at Beta's report in this same first report from Los Alamos in 1943 in March, here we'll see Beta's derivation or summary of diffusion theory of where these critical radius comes from. And if you use this is the critical radius. If you use this in a critical mass formula, you'll get the correct formula. And as I note here, Beta doesn't seem to make typos in his work. So not only did the formula have typos in, when you put the constants in, the cross sections in that they give, as I said before, you don't actually reproduce what Oppie quotes. When I take that formula and put in certain cross sections, what I find is that my numbers agree exactly with what Beta quotes when he does it, also with what the Maud committee was using. So they were probably using the same formula, though I don't know that for sure. And Oppie was off by 20%, but that was just, I think, some sloppiness. Let's just talk quickly about where this critical mass formula comes from. You will have come across some approaches in nuclear engineering textbooks. What I'm giving here is very crude, and it's not from diffusion theory, but I'm just giving you a taste of why it might have this form I just showed. So what is the critical radius? You might expect it to be dependent on the mean free path for a fission collision. But when fission occurs, you create more neutrons. In fact, nu bar -1 is the overall change in neutrons. And so that would be an inverse relationship. So you might expect the critical mass to be dependent on the mean free path divided by nu -1. So 1 over nu -1 times the number density times the fission cross-section. But likewise, you also might think it would depend on not just the fission interactions, but all collisions, because all collisions can stop neutrons from streaming out of the material. And so in that case, it's 1 over the number density times something called the transport cross-section. This is like the total cross-section, but it actually, anything elastic in the forward direction you subtract off. So it's a little bit less than the total cross-section for neutrons. In fact, if you go through diffusion theory, it depends on both these things as the square root of the product of them with a prefactor of pi over √3. And then you can do more sophisticated corrections which come in. But that gives you a sense of where this all comes from. And so the critical mass depends as 1 over the radius squared. I'm emphasizing that because that's important in the implosion mechanism we'll talk about soon, where you start off with material that's actually at natural density and spaced out, and you can compress it up to reach much higher than the critical mass because you've increased the density. And let's have a look. We'll compare here, just if you have a 235 sphere of uranium, how big is that? Well, I told you it was 46 kilograms, but that means its radius is about 8.8 centimeters. The two mean free paths we talked about here are of the order of 8 centimeters for the, 4 centimeters for the transport collision cross-section, and a mean free path of about 17 centimeters for the fission cross-section. But that formula works amazingly well. If you compare that number for pure bare 235 that I showed you with the simple formula, that gives 55 kilograms. That's actually 20% too high. In terms of the critical radius, which is cubed, it was only 6% too high. So really amazingly good. And that was just at the beginning of 43. During the project, characters like Feynman, von Neumann, Serber, this is Ulam actually here, but they had refined the numerical simulations tremendously. So they'd invented sort of SN neutronics, multi-group methods, where they were treating many, many more processes like capture and inelastic scattering and using polynomial expansions of the transport equation, etc. Okay, the story I'm going to tell you next, it really tracks the development of how we understood the critical assembly over time during the project. So these different descriptors here trace where things started, and this is for a bare 239 critical mass in its alpha phase. Alpha phase is the very brittle phase you have in the pure material at 19 point something grams per centimeter cubed. And rather amazingly, at the end of the project, they were using a number very similar to where they started, which is not so different from our best understandings today with MCMP and NDEF, for example. But during the project, their estimates were swinging all over the place as months passed by. So to give you an example, initially they assumed for the neutron multiplicity for plutonium, they hadn't measured it. They assumed it was the same as uranium. And they were starting with a number of 2.2, which turns out to be very wrong. We'll get to that later. That was actually 2.2 was a very initial measurement from Fermi for uranium-235. But Fermi did in August of 43 a new measurement in Chicago where he got a number of 2. Now, in hindsight, we know that this number actually got worse. When they did that, the lower neutron multiplicity pumped up their plutonium number substantially, up to near 30 kilograms. So this was very disappointing because it meant that they needed a lot more material to make a bomb. As time went on, we got better measurements of the multiplicity from people like Segre, which brought it back down again. The fission cross-section was measured for the first time by Segre for 239 plutonium, and it turned out to be lower than they had initially guessed. I think I told you that they started off with a very high number of three barns. And so this is Robert Backer, the division leader of the physics division. Every month they would have a meeting of all leaders of the lab with Oppenheimer to summarize where things stand. And in this August 1944 meeting, he had to share that plutonium cross sections must be revised down by at least 15%. So interesting to sort of see that documented. And I note here eventually it was more like a 30% decrease that they had to make. As time went on, they got better measurements of the multiplicity, and generally the theme was that multiplicity of measurements were great in terms of critical masses coming down. Fission was the opposite. You will have heard about the Jezebel critical assembly to actually measure this critical mass of plutonium. Well, that actually didn't come until after the war. So during the Manhattan Project, they didn't have enough pure 239 to actually make a bare critical mass measurement. The closest they got was actually the tamped critical mass of the material that was used in the Trinity test, that came really quite close to Trinity. Okay, so let's just look at critical masses of tamped materials. Typically, it's about just less than half of the bare critical mass. And for example, in March 1945, Robert Christie, the lead designer for the implosion, we call it Christie device, was calculating with his approaches a bare critical mass of about 5 kilograms. Today, with the best codes we have for I think this is the alpha phase here, we would get 4 kilograms, so rather close. If we use the delta phase, where some gallium has been added, this was done in the Manhattan Project. There's a fascinating story on that. It's unclassified that the metallurgists have heroes like Cyril Stanley Smith, who we physicists tend not to talk about. We talk about our Fermis and Oppenheimers and Betas, etc. But Cyril Stanley Smith was a remarkable metallurgist, also from Britain. He was working for the American Brass Alloy Company before the Manhattan Project started. And so he knew all about alloying. And they figured that by adding a bit of aluminum, they could make a material far more manageable and machinable than the delta phase. Turns out that aluminum was a problem because of the alpha N spontaneous neutron reaction that could cause a pre-initiation. And they realized that they could just go down the periodic table and use gallium instead. And so this has a lower density, 17 point something grams per centimeter cubed, this delta phase, and gives a critical mass slightly higher. Now, these numbers are unclassified about Trinity, that it had a delta phase with plutonium. Its mass was about 6 kilograms, and it had a tubuloy tamper. Tubuloy is still the phrase we use in Los Alamos for the 238 or the natural uranium tamper that was used. And you can see that their use of 6 kilograms here looks pretty bold, given that this calculation of the infinitely tamped critical mass is 5.5 kilograms of plutonium. Of course, it wasn't infinite, which is why this thing didn't go critical. It was close to critical, but it didn't go critical in its static configuration. As we started the experiments at the beginning of the war, people like Manley were in charge of the nuclear science program. This is also taken out of that initial conference summary. I won't go through it, but you can get a sense quickly of how they realized they had an ambitious project to measure all these fundamental constants of fission, capture, elastic scattering, inelastic, and so on. We'll talk first about the transport cross-section. As I said, this was really a sum of all non-elastic processes and all elastics except those in the forward direction. And the British, this is Sir James Chadwick, the British in their Maud report had already estimated that it should be about this amount. And the logic they used is beautiful and exactly right. And in fact, the number they got is very reasonable compared to the best estimates today. This traces the development of this transport cross-section during the project. And I picked out a number at about 1.5 MeV because that's a relevant neutron energy for these systems. This was the most likely number that they had. They also gave an estimate based on the most pessimistic number. Compton had estimated a number around 4 barns. At the beginning of the project, Oppenheimer was using 4 barns. And as time went on, they settled into a number that's very accurate compared to our best estimates today. This is how we would calculate it today. Heinz Barschel was one of the German emigres who came to Los Alamos via Princeton. He measured these cross-sections when he was here. I'm rather gratuitously showing a paper I wrote with him in the 90s. I had the privilege of collaborating with him for many years when he was at Wisconsin University in the 90s before he died. Okay, now we'll talk about the 235 important cross-section. This is where things ended up after the war, and Robert Wilson in his compilation from 1947 shows all these data, and you can see that around 1.5 MeV, they thought it was at that point about 1.33 barns. That's a little bit higher than where we are today. We'd say more like 1.2 barns here. Many of these data here are from the British. I've pointed out Frisch and Bretschke and Chadwick and Kinsey. Many measured locally. As we go forward, we'll be focusing on the 1.5 MeV slice, because that's the most relevant average energy of neutrons in a fast chain reaction. Oops. Here I just put on the points of where they thought things were before they started the project. So before they started the project, the colored points are all they knew, really. In fact, way up here off scale was a crazy number that was first guessed at by Frisch and Piles in 1940, 10 barns. There's a fun story associated with that I don't have time to tell. But as time progressed, by 1941, the British, these red points had already been measured in Liverpool by people like Frisch, and they were getting closer to the mark. Segre had made some measurements in Berkeley, these blue points. Heidenberg had made a measurement at Washington, D.C. at the Carnegie Institute. And I'd mentioned important new data that was coming from Wisconsin, from the Van de Graaff. These are these orange points here by Hansen and Benedict. And when the project started, Oppenheimer was quoting this kind of number around 1.6, 1.5 barns. As we'll progress over time, I'm now looking just at 1.5 MeV neutrons, and I'm plotting all these data as the project went on from the beginning, with Oppenheimer's guess of 1.6, which was, as I said, inspired by the Wisconsin value, with all the measurements that were made during the project at Los Alamos, some being sent from Britain by Chadwick and Kinsey, and by Bretschke, also working now in Los Alamos. Some measured with the Van de Graaff and cyclotrons, etc. at Los Alamos, in particular Williams's group here, which did some very good measurements, and Kuntz and Hall's group here. Now, they developed very accurate methods. Interestingly, virtually none of these data are in the sort of internationally available databases. The database that stores all cross-sections used around the world is called X4, and that's full of stuff after 1945, but these early measurements sort of aren't. And so one thing I'm going to do is get them into that database just for historical purposes. But you can see by the end of the project, they'd really got to very close numbers. Still a bit high though. So for example, our modern estimates from NDEF are informed very much by very accurate measurements, including, for example, Alan Carlson's measurement from 1985. I pull out this particular Kuntz. I'd like to emphasize that as one of the most accurate that was measured. a collaborator on that paper was Hall, picture of him here. And I really just mentioned that because he was one of the spies during the Manhattan Project. He was giving results to Russia, not as important as a scientist or as damaging as Fuchs, but I was kind of interested to see his name come up. The picture here shows Rudolf Peierls and Frisch. Now, in nuclear physics, we tend to think of Peierls as the, a remarkable man who got the whole game going for the bomb project and had calculated the transport cross sections and critical masses, etc. In fact, he was at Los Alamos the main leader of hydrodynamics, and he was brought in for his hydrodynamic expertise and led the Group 1 in T division under Beta. Beta referred to him as his most important group leader and successful group leader during that time. So he played a tremendous role in pulling off the hydrodynamics of the Trinity implosion, even though we nuclear physicists tend to think of him for our field. And in fact, of course, his main fame eventually was material science. So he was a remarkable guy. The Plutonium story is very similar. This is where things ended after the war, with the cross-section not at 3 barns, which Serber had said, which will be off the scale here when they started, but closer to just under 2 barns. And again, during the war at Los Alamos, the measurements ended up kind of coming lower and lower as better and better work was done. So we started off with these numbers like 3 barns estimates, but Williams was getting numbers closer to 2 barns. And I'd already told you about these reports that Bakker had to give that are in our minutes of these monthly reports in the archives downstairs from where I'm sitting. Newbar went the opposite direction. We started off with numbers that came in uranium. Well, these are very early numbers from France, etc., that were measured just after fission was discovered. And as better and better measurements were made, it started settling down. At the beginning of the war, we were driven by some numbers near just over 2 for the multiplicity from Fermi. I'm actually plotting thermal and fast measurements together. They do differ slightly, but not by a lot. And the differences are smaller than the main changes we're seeing here. Over time, better and better measurements were done that led at the end of the project to numbers that were much closer to the best values today. Likewise for plutonium, Newbar. At the beginning, they were just taking them from uranium. Later, they had the very first measurements. This was some notes I found in our archives in one of the minutes that was interesting, where the phrase heartening results were obtained. And this is where they measured for the first time the ratio of Newbar for plutonium to uranium, and found that plutonium was something like 20% higher, which was a sort of great news in the project. We'll talk next about the fission spectrum, the prompt fission neutron spectrum. So when uranium or plutonium fissions, it was known even from Serber at the beginning of the project that the spectrum looks something like this. It peaked at about 1 MeV, had a mean about 2 MeV. This is important. It affects the critical mass. It's also important in the time scale, tau, the time scale between fission collisions. This is important in the chain reaction. This is a quote from Beta. At the beginning of the project, I won't go through all this, but it basically says everybody knew that their measurements were terrible. They had real problems of backgrounds of various types. And so this is where things started at the beginning of the project. Ignore the black for the moment. Blue data were from measurements in 1942 from Rice University. So the red. The blue is from England, from Liverpool, Rotblat and Chadwick. And green is their estimate at that time. So a sort of average of those cross sections, this green line. Black is where we know the answer is today from our best estimates. And so you can see that their average energy was much higher. They actually knew they were wrong here because they had some integral measurements by Fermi and Christie, the same Christie who did hydrodynamics, but he worked at Chicago beforehand. He was actually a Canadian originally, interestingly. but he had measured the average energy given by neutrons as from fission as 2 MeV, and so they knew this was way too high. By the end of the project, things were much better understood. The black is where they are today in our best estimates. Red points are recent measurements from Los Alamos that have informed our best understanding. We call this the Kainu measurement that's just been recently published. But the black and red are where we are today. These other points of various colors were measured during the project. You can see that the measurement by Staub and Nicodemus, in particular in blue, is perhaps the best of the lot. I'm going to skip on here. The Plutonium Story is very similar. For some reason, the other measurements look better there. They agree with our best estimate much better. So a whole bunch of measurements had been done by the end of the project, which tended to agree reasonably well with our best understanding today in the black curve. There's some interesting history about, even at the beginning of the project, they sort of understood the basic ideas of where this functional form for the neutron spectrum should come from, which is basically the sort of evaporation process of neutrons from fission, but that then get kinematically boosted by the moving fission fragments to higher energies. I thought at first that Beta's summary in this 1943 was the nicest early estimate of the physics of what's going on. But in fact, in digging around in our vault, I found a document from 1942 sent by the British, a man called Norman Feather, who is often referred to as Chadwick's right-hand man. This document is our numbering system of British mission documents sent from Britain to the US as the collaboration was ramping up in the early 40s. And we can see here that in this screenshot from that early paper by Feather, he's talking about how the general features of the emission are capable of based on the evaporation hypothesis of Bohr and Weisskopf, but beyond brief references to the effect in papers by Bohr and Wheeler and Zinn and Szilard, no treatment of the influence of the motion of fission fragments on the energy spectrum of the emitted neutrons appears to have been undertaken. And then his paper goes and gives the basic math of that. So it's kind of really interesting, fun history. Okay, so I'll come to sort of the conclusion that we've tracked how these critical masses changed over the project based on improving understanding of nuclear science, and they really accomplished a tremendous amount in those 2 years. The cancelling errors are kind of amusing and amazing that they ended up where they started. This is for HEU uranium, but it's very similar to the Plutonium Story. And if we were to put uncertainties, though, on how we think things evolved, these are my estimates based on the uncertainties now. With hindsight, I can see. And basically, at the beginning of the project, even though they got the right answer, really the range, and this is just a 1 sigma range, for a number whose true answer is actually about 40 odd, ranges from 27 to 270 kilograms. That's a tremendous variation that they had to get their hands around. By the end of the project, just from the fundamental physics, they get this kind of uncertainty, much reduced. And in fact, that doesn't include what they then learned from their critical assembly experiments that allowed them to better refine their understanding. The critical assembly measurements of things like bare uranium were only being done in the early 1945 era, once they got enough material sent to Los Alamos. And Jessen Hutchinson is putting together an interesting summary of that era. Today, I would put our estimate on this number more like 1 plus or minus 1.7 kilograms. And if I allow myself to be guided not just by theory and simulation, but by the Godiva experiment, that drops to be 10 times smaller than this number. And of course, Trinity actually worked. It yielded 21 kilotons. That was actually much better than predicted. There's a fascinating story on why they predicted a lower value than what they got. I don't have time, or I'm not able to go into all those details here, but roughly speaking, if they'd actually believed their calculational predictions that they got, they actually got the right answer. They ended up being very pessimistic that everything would work out for the best, and they had various factors that they put in that they thought would degrade the explosion process. And in retrospect, they had made some remarkable predictions. And so I'll just end with a list of some of the sources that allowed me to put this talk together. Everything from a remarkable book that I would encourage you to buy called Critical Assembly. It's a technical history of the Manhattan era, produced by our historians at Los Alamos in the 80s. It is really quite remarkable and very, very useful. These are other resources that I've been helped by. So really appreciate you listening in on this, and I'm very happy to take any questions.
Awesome, thank you for that presentation. For the audience, as always, feel free to put your questions in the chat and I'll read them out. I'd like to start with a question from myself first, and based on your talk, it seems like the Manhattan Project was very, very lucky. So I was wondering if there were maybe any criticality accidents along the way, or any accidents in the too much material direction.
There were some accidents. There were a couple of sort of famous accidents that happened shortly after the war, and there were a couple of fatalities. And there was a man called Slotin, who was one of the, again, a Canadian actually, who was part of the British mission, who worked during the Manhattan Project. He was key to putting together the gadget and transporting it. And sadly, he died after the war. During the war, I'm not aware of anything. People like Jessen can give you much more details on that, except for one thing, which is that Frisch, in his memoirs, talks about how he was involved in developing this critical assembly of bare uranium, and he talks about how he noticed a neutron counter starting to rise big time when he got too close, and was able to very quickly move and survive. So I think there were some close calls, but that's my knowledge.
Cool, thank you. A question from Jake Carter in the chat is on slide 21, if you could maybe talk about the Tom Mason contribution.
Oh, yeah. I zipped through it fast, didn't I? Well, of course, Tom Mason is our lab director here at Los Alamos, and he came from Oak Ridge and knows the Oak Ridge history really well. But when I presented this locally, and he saw it, he commented that the time frame in the summer of 1943, when everybody got very depressed at Los Alamos because they thought Newbar was a lot higher. In fact, it really wasn't. It was a mistake. But Fermi's number had just come in, and that led to big requirements of a lot more separated 235 uranium. From his knowledge of Oak Ridge, that was exactly the time period when they got direction from Groves to expand their isotope separation plant infrastructure. And so the timing sort of fits.
Cool. Another question from the audience is from Sean Clark. It says, thanks for the fascinating talk. Can you comment on the understanding of delayed fission neutrons during the Manhattan Project and their role in the fast chain reaction?
Yes, that's actually a fascinating thing, and I haven't done it justice in this talk. In my reading, I come across it all the time, and they were very keen to understand the time frame on which neutrons were emitted. They had to be sure that they could understand how many were emitted in a very prompt mode for allowing a chain reaction, and how many would be delayed and therefore not able to sustain a chain reaction. I'm hesitant to say too much because I think it's a story that needs more digging into. Today, I know that we tend to think mostly about the delayed neutrons as a very important part of the sort of safety aspect of being able to make critical systems and reactors, etc. And they were learning that and had made tremendous insights into that. But that part of the story tends to be less of what I see rather than the impact on a fast chain reaction.
Thank you. A question from me is, I heard that you mentioned integral benchmarks a few times, and I guess I'm interested on how valuable, I guess, to NDEF data or any other data would differential benchmarks be, and how impactful would it be to know, I guess, neutron energy when performing these experiments?
Yes, so the integral benchmarks are absolutely essential, both for bare critical masses and temp critical masses, etc. If you talk about more differential benchmarks, the ones I'm most familiar are, for example, and maybe you can tell me more what you're interested in, but for example, we do have lots and lots of measurements starting in the early days on things like what's the within a critical assembly. So you've got a broad neutron source that's typical of the system you care about, a critical assembly or a weapon. You can put a small sample through the glory hole, as they call it, and that small sample you can measure, for example, fission rates in that integral environment. But it's a bit more differential because you're looking specifically at fission. You know, you're pulling out the fission process, and that's very useful for us because it's a kind of the result you obtain is a convolution of both the fission cross section and the energy spectrum in there, and so those kind of measurements are very useful. And Robert Wilson was quoting them extensively in the 1944, 45 era. So they were already doing those kind of measurements. Now, I know there are other types of integral, sort of semi-integral measurements. Are you thinking about some other ones as well?
No, I think that kind of answers the question. I was just thinking about, like, what are the next steps in improving nuclear data?
Yeah. The nuclear data we have today are understood in many ways remarkably well, and the challenge is that to improve them further tends to require, you know, new types of experiments with breakthroughs in precision or new novelty in certain types of experiments. So people are always thinking, are there clever integral experiments that could be done to better constrain what we know?
Thank you. I'm not seeing any other questions in chat, so I'll just ask, I guess, a less technical question as my last question. And when all the equipment was coming from all over the country to Los Alamos during the war, has it stayed with Los Alamos? Did it go back to these institutions?
Hey, that's
like, what happened? Yeah.
Yeah, that's a great question. I actually don't know the answer to that. You know, the equipment we have around for accelerators, none of this equipment is here anymore today. We actually do have a lot of equipment from the sort of 70s era, but from the 40s, it's not here anymore. Whether it was ever shipped back home, I don't know, but that's actually a great question I should know the answer to, and I'll ask.
Thank you. Yeah, I'm just curious. A question from Stephanie is, can you show again the slide where you talked about the spy and who it was?
Which slide, sorry?
Whoever, when you were talking about the spy.
Oh, yes, yeah. Here we go.
And then I guess the question was, who was it?
So this, can you see my cursor? This guy, Theodore Hall?
Yes.
Yeah, so some people, Alan Carr, in fact, is the master of the spy stories from Los Alamos. He's written extensively, and he's very knowledgeable about all the spies. Theodore Hall was one I'd heard the name over the years, but had never really dug into his particular role. In preparing this talk, I learned a minimal amount more about him, which is that when he came to Los Alamos, I don't know what the connection was of how he was brought here, but he was like, I think his claim to fame was he was maybe the youngest guy here. I mean, you can see him there. He looks like he's sort of 17 or something. But when he came, I think he was a very, very young chap, and like many people of that era. There were idealists who were worried about Russia being an ally and not being privy to the advances we were making here, and a communist sympathizer. And I believe he'd already made connections before he came to Los Alamos with Moscow connections in the States. So he already had a handler, and then ended up in Los Alamos and handed over information during that time. I'm sure on Wikipedia you'll be able to find out more about exactly how much he passed on. Klaus Fuchs, of course, is the person who came firstly from Germany to Britain for many years, and then from Britain he came to Los Alamos as part of the British mission. He was made a British citizen just before he came out to America. And he'd actually, in retrospect, we now know that he had been passing secrets on to Russia for many years before he came to Los Alamos. So I think from 1941 at least on. And he's the one who gave the blueprints of the bomb to Russia. And of course, it's known that Russia tested, their first test was a copy of Trinity. So Fuchs was both a dastardly spy who gave away really good stuff. He was actually a remarkable physicist and made really important contributions in everything from shock physics to ejector and spallation and hydrodynamics to isotope separation. So he was actually very widely regarded during the project by colleagues at Los Alamos. And there's actually a recent book on Fuchs by a British nuclear physicist called Frank Close that's just been published called Trinity. That's a great read. So if you like reading that kind of thing, Frank Close's book on Trinity is good.
Well, thank you. So it looks like those were all the questions, and we're right up on noon. So I just wanted to say thank you again on behalf of the monitoring technology and verification consortium, and just everyone here. That was a really interesting talk. So thank you.
Hey, great. Well, thank you so much. Enjoy your days.
Thank you. All right. Goodbye, everyone.